Today we're going to follow up on the exploratory data analysis module by showing you some plots to avoid. So this lecture is courtesy of Carl Broman, who has put up some code to produce some of the good versions of the bad plots we're going to show today. So a lot of the plots we're showing today have become very common in the scientific literature, and it's partly due to the fact that they are default plots from Excel. But today we're going to show you ways in which you can show more informative versions of those plots by using R and Bioconductor. All right, so what do we want to do when we show data? We want to make plots to convey the characteristics of our data. We want to display data accurately and clearly. And we want to provide, in this lecture, we're going to provide some examples of the bad plots and then the improved ones. So here's the first one, the box plot. They're very common in the scientific literature. Here I'm showing you the browser usage from August 2013. And what I want you to try to figure out is just from this figure, I want you to figure out the percentages. So just look at the figure and tell me what percent of users use Chrome or Safari, etc. So it turns out that humans aren't very good at determining area, relative area. Here are the actual percentages for those that try to do it at home. And a much better way to represent these numbers is, one, you can just show the numbers without a pie chart. You can save the journal some printing costs. And if you do want to show it in a plot, then the bar plot is actually easier to read. For example, if you want to know how many people use Chrome, you just follow the line and you figure out that it's 44%. That's much easier than trying to determine area. We also see these bar plots in 3D, but that really doesn't add much, and in fact makes it a little bit harder to determine the actual height. So that's not something we want to see. All right, so another plot that's very common is a bar plot to summarize several data points. So this figure is showing us data from treatment and controls. And we see a little antenna on top. It's also very common. The antenna usually represents the standard error of the data. So this data is actually, we can actually show the points because it's based on just a few numbers, and this is what it looks like. So you can see that you can actually see the spread of the data that you collected. So here's a comparison. You can see how much more we learn from the figure on the right than from the figure on the left. Another problem with the figure on the left is that it starts at 0. So you have all this space that is actually not necessary to represent what's actually going on. When we have more data, we can make box plots instead of plotting all the numbers. Another very common problem that these types of plots result in is that we don't see outliers. So here's some data represented as bar plots. And it appears that the control group has much higher measurements than the treatment group. When we actually plot the data, we see that it's actually driven by these 2 points here. And if we change the scale of the plot to the log scale, we see actually what's going on. The treatment and control are in fact somewhat different, but that first plot was quite deceiving, as is shown in this comparison. A third, very awkward plot that is made by Excel is these bar plots to compare two numbers. So here we're comparing pairs of numbers. So we're comparing, this is actually just showing us 6 pairs of numbers, which a much natural way to show is to just make a scatter plot. And now we can actually see that there's maybe a little bit of an increasing trend in when we compare before and after. So the last recommendation we're making in this module is to know what precision you're working on. So many times this actually comes out of R or other analysis software. They spit out numbers with a lot of digits. And of course, when you're working in science, you actually don't have this much precision. There's really nothing that you gain from adding these last digits. So you want to know what your precision is, and you can make the same table showing the actual information that you have, and it becomes much easier to read. Here's a comparison of the same table, one with the correct precision and one with extra precision. So those are some recommendations of simple things you can do to improve the way you display data. In the next modules, we're gonna give you some examples from genomics. And also, we're going to explain why Pseudo 3D is not a good way of displaying data in general.